Hello, everyone. Welcome to the MIT IoT Seminar Series. It is my great pleasure today to introduce Dr. Bruce Howe. Dr. Howe is a professor at the University of Hawaii at Manoa, and he is the chair of the International Task Force, a joint task force on smart cable initiatives. Dr. Howe develops ocean observing infrastructure for the provision of power, communications, and positioning throughout the ocean volume with an emphasis on cabled and acoustic systems. He is currently leading the effort to incorporate sensors into commercial trans-ocean submarine telecommunication cable systems, an effort that I'm very excited that he's agreed to join us today and share with us. Over the course of his career, he has made many similar contributions in ocean observing systems. And prior to that, he obtained engineering and oceanography degrees from Stanford and UC San Diego, and worked at the Applied Physics Lab at UW since 2008, and since 2008 at the University of Hawaii at Manoa, Department of Ocean and Resource Engineering. Dr. Howie, thank you so much for joining us. Very excited about your talk. The screen is yours.
Okay, thank you, Fidel, and thanks for the opportunity to talk about smart cables. As said, SMART stands for Science Monitoring and Reliable Telecommunications. And this joint task force is sponsored by 3 UN agencies: the International Telecommunications Union, World Meteorological Organization, and the UNESCO Intergovernmental Oceanographic Commission. And we just received endorsement by the UN Decade of Ocean Science for Sustainable Development. Here's my outline. Kind of a standard one: what, why, how, and describing some systems underway and the steps we're taking. And then I've actually added a little here, essential deep ocean infrastructure, sort of as an extra. And I'm going to ask you before I actually get in that section, what you think the essential infrastructure is. So you can put that in the chat window. So next, this is a kind of a overview summary slide, so I'll spend a bit of time on it. The goal here is really to create a global array that addresses climate, ocean, sea level, earthquakes, and tsunamis. This is basically creating a planetary sensor network with power and internet connectivity. If we succeed in doing this, and we're right on the cusp of starting really in water, this will really be a first order addition to the ocean and earth observing system. And it all depends on sharing this subsea submarine cable infrastructure, telecom plus science, in order to reduce cost is a large part, and just from practical considerations. One of the absolute requirements is that there's no interference between the science component and the telecom component, so that the telecom mission has priority, is a primary mission, and science secondary. So decisions are made to make sure that the telecom system continues to be robust as it is now. The map shows roughly 1.2 or 1.4 million kilometers of seafloor cable, roughly 400 individual systems, and nominally 20,000 repeaters every 70 kilometers, say. And there's rough 10 to 25 year refresh cycle. So the engineering life of these systems is 25 years, but typically the cables along more active routes are replaced sooner because of financial reasons, really. And the sensors we're talking about installing initially are bottom temperature, pressure, and seismic acceleration. The very simplest ones: small, compact, robust, well proven. And you know, these will not only provide the science and early warning data, but they'll provide data to help the cable systems themselves. If the cable systems themselves know their environment, they can be better protected, and thereby benefit their mission of providing connectivity. I'll say a few words later on this CAM system in Portugal. These circles represent systems under discussion or and starting the CAM system here off Portugal is approved by a government, and they're appropriating money at this moment. And it'd be 3,700 kilometers with roughly 50 smart repeaters connecting Lisbon, Azores, and Madeira in a ring. Okay. So let's see what we're actually going to measure with this system. Again, those three basic measurements: temperature, pressure, and seismic acceleration. Temperature, the map on the top right shows the deep ocean temperature measured by ships. Each of these lines there is like every 10 years a ship goes by and makes these measurements. So we would be providing deep measurements on a continuous real-time basis, and obviously measure deep ocean warming. And then also, as the ocean warms, it also expands, and therefore sea level rises. And this affects circulation and climate. The middle picture shows sea level rise millimeters per year over the last 25 years or so. So it's variable, time dependent also. As ice melts, the circulation of the ocean will change. And that's reflected down here in the lower picture. With bottom pressure, you can estimate what's called the barotropic component of water velocity. Basically, water flows from high pressure to low pressure, gets turned by Coriolis, but the basic thing is that it's measuring a component of the ocean circulation with the pressure. And then also just sea level rise. More mass from melting water will increase sea floor pressure. And then from a hazards point of view, obviously pressure measures tsunami waves passing by, and the seismic accelerometer is a poor man's seismometer, broadband seismometer, and both of those together will help improve the tsunami warning process. And then lastly, just from a scientific point of view, we'll learn a lot more about the solid Earth with these measurements, because we're putting sensors in that'll provide data in the 70% of the Earth's surface where there are no sensors now, basically. Okay. What happened here? Okay, so why are we doing this? I mean, this hopefully is review for everyone, but it doesn't hurt to review. Global warming is accelerating. We're at 1.2 degrees or so warmer than pre-industrial, and the last 6 years have been the 6 warmest years on record, and the trends are steepening in these last 6 years, and effects like El Nino and La Nina will affect this as well. And I say here in the other slides, the ocean is the flywheel of climate, and we really need to know all the intimate details of ocean flow and characterization to better predict the climate changes that'll affect the human state. Again, everyone's seen these curves, historical CO2 emissions. What's slightly different here, and I recognize Chip Fletcher here at UH providing these, is simply the horizontal scale. He's compressed that, or in this picture it's compressed to truly show the exponential rise in emissions, and then more importantly, what we have to do to reduce the effect of these emissions, and showing the time scales that we have to do these things in. So, you know, when at the COP meeting now, you know, we need to reduce emissions by 2050. Well, this shows the challenge we have of trying to reduce emissions that, you know, have been growing exponentially for the last 100, 200 years or 1,000 years. But to do it in just a few years is going to be extremely challenging. And then another aspect here that I think people don't appreciate, there's so much talk about, average global warming. Well, in some places, the land temperature is going to increase such that you simply cannot live there. And so by 2070, the projection is 20% of the land surface will be too hot for human existence. So think about that, 20%. And it's not just, that 20% area, it's, that's a spillover beyond that's really disturbing, let's say. So just kind of summarizing here, climate change is humanity's greatest existential threat now. And this is, being debated in the COP26 meeting going on now. And we will be addressing this, in our small way, the societal and environmental issues within the UN Decade of Ocean Science. So addressing climate change, SDG, Sustainable Development Goal 13, by measuring ocean temperature, circulation, and so on over short and long term. Sea level rise, addressing ocean SDG 14, hazards for coasts and islands and cities, and disaster risk reduction, the Sendai agreement, and so on. And I mentioned here down at the bottom, social connectivity, so and SDG 9 and 11 that address infrastructure. So by improving the submarine cable infrastructure, by better understanding the environment it exists in, we can improve connectivity, we can improve the performance of that system, and thereby provide societal benefit as well. So just to hammer home this aspect, we are absolutely addressing components of the UN Decade of Ocean Science, both these 5 challenges, ocean and climate nexus, early warning services, and sustainable ocean observing system. Like early warning, sea level rise. Again, we talk about slow, gradual changes, but you consider shallow slopes of seashores that, even millimeters of water will extend horizontally quite far, or a few feet of change will eat away at cliffs even, and cause collapse and so on. Let alone for ice shelves, changing ocean, eating away at the face of an ice shelf and ice cliff. So providing early warning for earthquakes and tsunamis, and mitigate coastal flooding. And then absolutely we'll be contributing to the global ocean observing system. Okay, so how are we going to do this? We're not just starting from scratch here, obviously. First, the submarine cable industry is 170 years old. So, we're drawing upon that level of expertise and experience and 25-year lifetime, engineering lifetime. I mean, in anything oceanographic, that's a worthy goal to achieve. More directly, though, we will be basing smart cables on these dedicated cable systems that I show here. The Japanese SNET and Senriku systems, and which have inline instrumentation, so there are no connectors involved. And then DUNET, another Japanese system, where there is higher power, and also the Neptune and OOI systems off the west coast of North America. So the latter can provide more power, quite a bit of power, but they also need remotely operated vehicles, which are quite expensive to operate. The Japanese are presently installing yet another system off their coast to the southwest of DUNET to cover more of the Nankai Trough, called NNET. So that system is supposed to be a kind of hybrid, both having inline sensors in the units along the cable, and then also have these nodes where ROVs can attach more specialized instrumentation. I mentioned in the lower left figure, the Senriku system, and I'll show a picture later from that, but it's basically something quite close to the SMART concept, with a low cost couple of sensors in a repeater housing. And this particular system's a University of Tokyo research project. So here's some sort of nuts and bolts way how we'll approach this, and it's still up in the air to some extent. It's going to depend on the first system, what the supplier of the first system will actually implement. The Joint Task Force has refrained from saying or giving specifications of how to actually do it. We've given functional requirements and so on. But these are two possible approaches to installing sensors. So this is on the top left is a repeater body. You can see a whole bunch of them lined up. I think this was the Brazil to Angola cable system, all stacked up in a warehouse. So that gives a scale for what one of these repeaters is, about a foot diameter by a meter long. And so the seismometers or accelerometers can clearly exist inside this housing. They do not need to be in contact with water, whereas the pressure and temperature sensors must be in contact with water in one way or another. And so they could either be on the inside the end bell and end cone, or offset in a separate sensor blister, if you will, or sensor pod. So as the first systems like Portugal are going to be done, we will learn how that particular supplier intends to do it. Okay, so here are some of the systems in progress right now, and I'll show a few pictures on some of these. There is another wet demonstration project similar to Senriku in progress right now off Sicily. I've mentioned the Portugal system. Indonesia is developing in-country expertise. There's a Western Mediterranean system, and I'll show that. French Polynesia request for proposal is in progress. And Vanuatu, New Caledonia, there's progress there. And in New Zealand, last February, there was a workshop to discuss a possible smart cable system between the main islands and Chatham Islands, small population. So again, the primary purpose is connectivity to that community, but along the way, they're suggesting installing smart capability as well as other sensing capability. So that's in progress now. And then these other ones off Australia and in the Indian Ocean and Arctic Ocean. And then similar to New Zealand, there was a workshop last June on a cable suggested from New Zealand to McMurdo Bay to, again, primary purpose is provide connectivity to the scientists and logistics on Antarctica, and at the same time explicitly make that a smart cable to provide information about the ocean in between. Lastly, just mention that Alcatel Submarine Networks, ASN, has issued a press release indicating that they will supply smart capability. And as these RFPs require smart capability, they are prepared to provide that. Okay, so just a couple of pictures on some of these different systems. The wet demonstration off Sicily. This is Sicily on the left here. There's an existing small cable system there, plug and play, shared with neutrino physics people and geophysics. And so the intent is to install 3 repeaters with sensors, but not with the telecom mission, to demonstrate that one can get useful science data out of these systems. They'll have other sensors around for validation. This shows the New Zealand Chatham Island cable route and smart repeaters, and then also these dedicated nodes, and I'll talk more about that. The new Caledonia Vanuatu system crosses a trench, and the scale is kind of perfect for scientific study. Vanuatu is one of the top 2 countries with the most earthquakes and disasters in the world, and this is a young subduction zone trench and fault system, so it's scientifically very interesting as well. And this shows the Antarctic system. I sort of tease you with this unusual map projection. It's called a Spillhouse projection. It basically shows all the coastlines around the ocean, and then sort of the ocean is one contiguous body here, and it's centered on Antarctica in this case, and this little green section is the cable that's being talked about. So there is a National Academy of Science effort underway now to hold another workshop in March on this, and then to write a report with concrete recommendations. This is the Mediterranean system I've mentioned, going from Lisbon, Barcelona, Marseille, Sicily, Crete, and Egypt, and with up to 60 smart repeaters. And this would be a tremendous improvement. Right now, there are no DART tsunami warning buoys in the Mediterranean, and yet there absolutely have been historical tsunamis in the Mediterranean, and earthquakes and so on. So this would be a great boon to the region to have this, but we're in the process of raising those funds now. This shows the Portuguese system a little in more detail. The black cable here, some of the earthquakes along the mid-Atlantic ridge and in the Azores, and then around Portugal. So they are motivated, strongly motivated by the 1755 earthquake tsunami that basically destroyed Lisbon, and in the process, and much of the coast infrastructure and lives, but it basically brought about the downfall of their empire. So they are very sensitive to this and understand the need for it. I just mentioned here that MIT does have a program with Portugal, so we're hoping something might come out of that. There is a science group that's been set up to address the provide scientific requirements for this system and interact with the implementing organization. And this is the kind of some of the simulations being done to rationalize this from a government point of view, or something governments can easily understand in this situation. Again, the 1755 earthquake. So simulations basically of earthquakes. And then in this case, Vitor Silva has simulated how many lives would be lost without this warning, early warning for earthquakes, and then how many lives would be saved by adding even tens of seconds of earthquake warning. So he concludes that 90 million euros savings in cost if there was one of these kind of events during the 25-year lifetime. And he's only simulated the earthquake portion and not included tsunami, inundation, and so on. So that would make it even more clear. I just mentioned down here that for reference cost, a DART buoy, this is basically a bottom pressure sensor, acoustic link to a surface buoy, satellite link back. They cost 500,000 euros per year to operate and maintain. In this case, for the given geometry, basically is 25,000 euros per year per repeater node. So much less expensive overall. So we're following several strategic paths here, trying to implement the SMART concept. As one of our sponsors, ITU, has been very helpful, and especially Portugal in pushing forward a SMART cable resolution that will be presented to the World Standardization Assembly. So this is all member state activities. These are UN organizations, so these are being approved by member states. And then they have entities called study groups that address questions. I mean, they write requirements, recommendations for Ethernet, precise timing, 5G and so on, and they're going to work on similar documents for both smart cables combining with telecom as well as dedicated cable systems. And then furthermore, they're going to amend various resolutions already on the books for climate and disaster risk reduction to include smart cables in those. Then shifting to UNESCO IOC, the assembly there has approved the development of a tsunami program for the UN decade. And this will hopefully pull together all the tsunami warning aspects within IOC and all the UN programs. And smart cables are explicitly called out in that program. And as I said, we've just been endorsed by the UN Decade of Ocean Science Project. So I say again that when all these activities are underway with member state approval and these resolutions are passed by member states, we'll have a much stronger foundation. And furthermore, when that happens, these organizations will be empowered, enabled to provide us more support financially and manpower wise in trying to move this forward. So as chair of this group, I give presentations. These are the last year or so, and here's MIT down here towards the end, but trying to spread the word and so on. And we have a paper in under review in Frontiers of Earth Science. Just coming to a close on the smart cable part, I want to emphasize that there's sort of two aspects, and I've used Portugal here to some extent as an example. First of all, scientifically, it'll contribute to understanding marine overturning circulation, large scale circulation of the ocean. And part of that will include observing system simulation experiments, and people at MIT do this, Pierre Lemousseau and then John Marshall, and then in Portugal also there are people doing this. So I'm hoping that there can be some collaboration there. And then there needs to be cross-calibration and validation between cable observations and other observations. Another aspect of this we haven't touched on yet, but is really to manage these economic zones, one needs data. And so this can help provide that data. And as there's more and more attention being paid to illegal fishing, and so perhaps by including hydrophones, we can and passive acoustic monitoring, we can help in detecting ships running without AIS and so on, and acting illegally. And then furthermore, really my hope is that by putting in smart cables, which are basically measuring some very basic ocean parameters, that they can catalyze other activities that will build on that and get more measurements of different kinds and so on. And so catalyze new cables, reusing old cables as cables are retired, and adding more detailed observatories, and especially adding docking stations for AUVs so that one can extend the spatial footprint out away from the fixed cables. So again, using Portugal as an example, we really want to survey, for instance, all the volcanic spreading zone features within the Azores region, but then also think about the entire mid-Atlantic ridge and the mid-ocean ridges, you want to measure those in much more detail than otherwise. And then acoustic navigation, not smart cables, but other cables could support aspects of that, and in the process support tomography and large-scale ocean temperature monitoring. Also, there's a new measurement technique underway now called optical fiber sensing, and these cables will catalyze a lot of development in that area. And just lastly, the tide raises all ships. So, one project succeeds, like hopefully smart cables will, all these other things can also move forward. So in conclusion, I think smart availability will be commercially available in the 2024 timeframe, installed, ready for service in 2024, 2025. And these early systems like Portugal will be setting very valuable precedents on how one actually runs a project, gets money for a project, and shows that it works technically and doesn't interfere with telecom and things of that nature. And these will be laying the foundation for more complex systems in the future. So smart cables can catalyze other developments as well. So here, I'd like to shift gears really to this second absolutely related topic on deep ocean infrastructure. I'm a co-PI on a Excel network project, NSF funded, called Implementing Deep Ocean Observing Strategy. So it's all about organizing and facilitating, not actually hardware or anything, but still, how do we get access to the deep ocean? So if anyone wants to speak up quickly or put in the chat window what you think are the primary attributes of deep ocean infrastructure, both from a service point of view or element point of view, feel free. Although the next slide will basically give my view of it. And this is a kind of a new, a new section to my talks, and I'm still developing this, so bear with me. And it does absolutely reflect on my background, and so I show a few pictures of, I've been involved in long range acoustics and underwater gliders and mobile platforms and absolutely cable systems. So that does influence my outlook on this topic. But anyway, what I'm thinking of here is that we to accomplish any observing especially in anywhere, but especially deep ocean, and even on land or whatever, we need power. That is the fundamental thing we need. And everything depends on power, and power enables everything: communications and what's called PNT, positioning, navigation, and timing. All of that requires, in our world now, electrical power. And then those are services, and then elements actually implement those in one way or another. So cables, fixed platforms, and mobile platforms are all part of the picture. So again, what are the essential global scale observing infrastructure services we need? Again, power, and it's really considering the entire power as a function of X, Y, Z, and time. So you can consider an AUV as being a source of power, but its X, Y, Z is changing with time and so on, but it can provide power not only to itself, but to other things as well. So that's the idea there. And then cables, obviously, are, they're fixed in space and mostly in time. But again, power enables communication and PNT. And then of course, that enables things like charging electric vehicles, whether they're cars on land or AUVs in the water. It enables motion basically, and then obviously electronics, and then wherever you want to heat things or cool things, and provide light for video, for instance, power is needed. And in many of these cases, it's substantial power. And again, these ideas apply to space, air, land, ocean, irrespectively. And what I'm saying is the deep ocean is special. For space, air, land, and upper ocean, these are somewhat easy areas to provide these essential infrastructure services. At the ocean surface, there's alternative energy, solar, wind, wave. You have access to the electromagnetic spectrum for communications, radio, GPS, and you can charge vehicles, for instance. But when you want to extend infrastructure into the deep ocean, you quickly come against real problems. And what I'm suggesting is consider sort of, to some extent, early rural electrification. So when electric power was first supplied in the US or elsewhere, one of the first things that it powered was electric or water pumps, lighting, battery charging, refrigeration, and communication. I mean, access to simply listening to a radio, let alone telephones and so on. And I saw this, my wife is from Thailand and from a small village, and their first electric line in the early 80s was, a little extension cord to the neighbor. And the first things they had were a fluorescent light and a radio. Then came a water pump, and then came a refrigerator. So, it's the same idea in the ocean of how do we provide this? And this translates to the deep ocean, which is not easy, like near the surface and on land. And so what's the difference? Well, and this is kind of an important topic that I probably should devote a little more time to, but is in the deep ocean, there is no appreciable energy. There's no sun. There's effectively very, very little kinetic energy. And then any umbilicals, whether cabled or tankers like AUVs going from surface to bottom, are largely impractical. And there's no large scale communication system or positioning navigation system in place. So again, I come back, is probably not surprising, but suggest that a core network of power and telecom cables in the SMART concept be extended, basically sharing this infrastructure to provide these essential services. One way to look at it is submarine telecom cables already have power and communications inside them, and we just need to break that out into the open more explicitly. And so I'm suggesting hybrid systems, smart cables for sensors to get global coverage, and then powered branch units or branch nodes to break out power and communication to seafloor users to support, for instance, AUVs, moorings with acoustic sources for long-range GPS. And obviously these are going to cost more, so there'll be fewer of them. But even if they're on a 2,000 kilometer scale, that's a lot better than now. And then local, and these would support local infrastructure around each of these nodes, and supporting fixed platforms, bottom packages, subsurface moorings, for instance, and mobile platforms via docking stations for AUVs, rovers, with dependable charging on the seafloor, with navigation for these mobile assets. And again, influenced by my background, a product of acoustic GPS underwater would be acoustic tomography for heat content. So if you can do underwater navigation, you're effectively doing tomography to measure the ocean heat content by measuring travel time between sources and receivers. And this would complement and absolutely improve large-scale ocean heat content measurements over, for instance, Argo floats. So some of this is based on these two recommendations from Ocean Obs Conference 19 to implement smart subsea cables and multi-purpose acoustic networks. So again, I'm suggesting a systems approach here. One really needs to look at all of these aspects carefully and optimize it, keep it simple. So the fewer moving parts, the better. But at the same time, it has to scale to global scale, and then plan for decades and really centuries into the future. And again, here, sharing having cables as a foundation, element of this, and taking advantage of this $5 billion a year industry with so much experience is something we all should be considering. And really, the cable industry has been the sole benign users of the deep sea floor for the last 170 years. And furthermore, optical fiber communications appears to be the only way of truly high bandwidth communication connecting our civilization together for the foreseeable future. And so, we want to tap in literally and figuratively into this valuable resource. So via smart cables, and then this is a new development. This is one supplier has said they will be making delivering what they're calling a power transfer unit that will be telecom rated. In other words, can be inserted into a telecom system. So like here, standard telecom, standard branch unit, and then this power unit would deliver local power and communication on significant scales. So kilowatts of power at high voltage. Well, the trunk is at high voltage, and so on. I do make a comment here that in many of these cartoons, they're still cartoons. We've been drawing cartoons for the last 25 years like this, but and AUV docking is in all these cartoons, and it's still somewhat elusive. There are a few out there docking, but we need to do better there. But I'm anticipating that in the nearer term now than it was 25 years ago. So this would be a crucial aspect of this concept. So I'm coming to the end here. This is this Senriku system, which is an in-between hybrid alternative. In this particular unit, one of three, they actually have a hose coming out to an underwater mateable connector. And when it's deployed, it's in this frame. And so it's one connector with power over Ethernet. So one could connect something to that, whether it's one specific instrument or a small docking station or a small collection of instruments, that's TBD. So there are these technical options. Lastly, on acoustics, multi-purpose acoustic system. This is from Kevin Heaney, showing a map of the global ambient soundscape, and then what the sound level would be relative to this for adding two acoustic sources, one off Hawaii and one off the Pacific Northwest. And one can see that the sound levels are at most equal to what's already out there in the ocean. And this would provide 2D navigation over the areas where these two sources overlap. So just a few sources could go a long way to providing basin scale navigation and at the same time heat content and temperature measurements. And then the other thing is one can then, if Argo floats had hydrophones on them, one could measure their velocity very precisely each for every single transmission. So rather than waiting 10 days between GPS fixes, one can get it, let's say, every other hour or something. And this shows one of the more recent acoustic sources deployed for a year in the Arctic as an example. So in summary, and this comes from a OECD document, expanding the use of sensors could be substantially made by integrating them into telecommunication cables, power cables serving offshore wind farms. Alone, the global subsea communications network of over 1 million kilometers offers vast opportunities for installing more sensors, given that parts of the network require renewal and replacement. So with that, I'll conclude and open the floor for questions. Thank you.
Thank you very much, Bruce, for a very exciting vision and all the work that you've been doing in this space. If people want to ask questions, please feel free to unmute and sort of turn on your video. You can also use the chat. Also, thank you for like perfectly timing it on time as we discussed. And yeah, as I mentioned, if people want, they can unmute or raise their hand and ask. We can unmute. Now you should be able to, Jack. You cannot. What about now?
And now I can. Okay. Hey, yeah, Bruce, I had a question. So I'm curious about the just the practical installation of these cables. Like with the actual fiber optic cables, the repeaters themselves, can they do you have to lift up the whole cable out of the water and replace a new your smart cable onto it? How do you actually attach it in the water?
This is all for new systems.
Okay.
It's not replacing anything in the water now. That's just too expensive. So it's new systems, but they're new systems going in all the time. There's 50 to 100,000 kilometers of cable being laid every single year. So there's plenty of opportunities to do this. Now you may have to wait, for a number of years to get a cable in the area of your particular interest or whatever. But in general, the idea is over 10 or 20 years, sort of random installations, we will end up with a global scale coverage.
Right. Cool. Thank you.
Thanks, Jack, for asking that question. I was also wondering whether you need to take systems offline in order for you to add these. Yeah, if people want to ask questions, please feel free to unmute and ask. I have a number of questions that I'll be asking along the way. All feel free to use the chat and we can read and answer them. Doug, would you like to ask a question?
Sorry, Bruce, excellent, absolutely excellent talk. I really enjoyed it. A question, how far along is the sensor technology for these kind of depths? I've been stalking you and listened to a number of your online video talks in other contexts. And one of the questions that came up was, how do you maintain calibration on some of the depth sensors and things like this?
Yeah. So the temperature and the accelerometer are reasonably well positioned from a calibration and a very small drift point of view. The pressure sensor, the current best pressure sensor, does have drift, and it should have oceanographic calibration, cross-validation, if you will, done. So for instance, Portugal, if one runs a CDD section along the cable once a year, the expectation is that should be adequate to nail down the drift. The drift is somewhat, after some time, obviously predictable. It's an exponential plus a linear, so there are two terms. But and with 50 sensors in the same vicinity, one expects that can be handled, let's say. And this is done routinely for inverted pressure inverted echo sounder systems, is to basically cross calibrate them against like satellite altimetry and things like that. But you're right. We would like a better pressure sensor, and we're talking, you know, millimeter per year kind of drift. Right now, it could be 10 centimeters per year initially, but then flattening out. You know, for tsunami warning, this is not an issue by any means, but to really get, you know, climate scale changes, it is a problem. So we're open for suggestions. there is one pressure development called A0A, where it shifts the input to the pressure sensor to inside the pressure case, air pressure inside, and use that as a reference. But that's, you know, kind of an awkward, inelegant, you know, hydraulic valve and stuff. But you're right. And then for, you know, biogeochemical or biological, ecological sensors, they just simply are not ready for deep ocean 25-year life. So it is a problem. And that's where AUVs, for instance, you know, if one included docking stations, one could, well, first of all, one can use AUVs to cross calibrate things as well. But they can also carry these more difficult sensors, if you will, you know, and at least recharge down on the seafloor and continue emission and so on. So it may be that AUVs carry the more difficult sensors, and the simple ones reside for a longer time based on the cable.
Thank you very much. Just another question, if I may. You've specifically chosen tsunamis as the first main application, and I assume because of the high value. Are there other sensors? You know, are there other? If you had to add to what the next sensor other than pressure and acoustics would be, you mentioned these temperature measurements by acoustic transmission as being the next one. What other high value applications do you see that could drive more sensor technology in these cables?
Well, again, it's sort of the infrastructure. As you say, hydrophones would provide a lot of more data and contribute to a more complete acoustic network. But I think probably the next thing should be an acoustic modem. So it's not really a sensor in itself. It could be made into an inverted echo sounder, but it would enable, you know, real-time communication with nearby instrumentation. So, you know, it's not just about sensing, but again, it's providing infrastructure. So, you know, and then other things, ADCPs, and again, it's, you know, things that are robust and long-lived. So there aren't that many of those sensors, but it's things of that nature, I think, that should be next.
Thank you. I have to run to another.
Yeah. Okay.
I have to run to another meeting, but I would love to give you a call and talk more to you.
Great.
I greatly appreciated the last time you talked with me. So.
Okay. Good.
Thank you for an excellent talk.
Thank you for a great talk. Likewise, I got to run, but I'd love to chat more. Thank you.
Okay. Thanks, John.
Yeah, we have time for a couple more questions. I have a question, Bruce. Towards the end, you also talked about like these docking stations. What are in general the bandwidth and power sort of requirements for these types of deployments, and to what extent are sort of telecom providers okay with adding this? Because it does take from the power that is otherwise going to go to the repeaters. It does take some bandwidth. And what is sort of acceptable for them to deploy?
Okay, so first of all, this power transfer unit, I mean, this is the first unit's going to be delivered next year. So it's not as if it's widely considered at the moment. I'm suggesting it should gain a little more prominence. But well, and you saw the development for the smart repeater aspect of how willing the telecom is to assimilating that. And it's like pulling teeth, frankly. And we were amazed and pleased when Alcatel came out with an announcement, but the other four major companies have been very quiet. You know, they just say, well, when we see commercial demand, we'll do it. But for power, you know, well, first of all, AUV charging, you know, it can be anywhere from tens of watts to kilowatts. And so it's a full range. And I guess my personal feeling is one wants to get away from large AUVs that are exceedingly expensive and basically military. And we want to be able to enable things like REMUS, you know, or smaller units that maybe can go 1,000 kilometers between charging stations. But from the point of view, a technical point of view, cable ratings are now 18,000 volts, the voltage rating. And these cable systems are typically double end feeds. So there's really 36,000 volts across them. And they operate at 1 amp. So you have 36 kilowatts. So presently, systems use about 100, or the longest systems use about 15 kilowatts. So if they really push the limits, they could get another 15 kilowatts, for instance, and that would have to be divided up however, you know, is appropriate. And the other thing to keep in mind is the amount of power the telecom needs, number of repeaters, is proportional to length. So one could start with shorter systems that could provide more power, relatively speaking, to science. And you know, one would have to pay for, you know, larger power supplies on shore, obviously, than otherwise. But you know, that's part of the equation. Does that answer?
Yes, great. Thank you very much. And yeah, thanks for everyone for joining us today. We'll wrap up the seminar now. Thanks so much again, Bruce, for giving us the talk, and for all of your work leading this effort.